All right, now that we have Gnuplot, you might be asking, all right, why do we just go through learning that? Well, we want to come up with empirical measurements. I want to make sure y'all see that certain programs do actually behave or are slower than others based on the way you program them. And empirical means, let me make sure I had one student had a problem with this lesson. So empirical means we are actually collecting actual statistics, real life statistics. Theoretical measurements are what big O is, where we're doing analysis and trying to come up with what we believe it's going to behave like. So, whenever I say empirical, I mean you have to collect actual data. So the analytical or the theoretical measurement of performance is important because it is very important, but sometimes empirical approach is far more useful. Especially, I think it really drives home the performance of these different data structures. The naive way to take timings. So is record the start time, run your code, then record it end time, and your answer is end minus start. All right. You all see how that's probably the most intuitive way and the simplest way to do it? All right. There are numerous issues with this approach. You will find out more of those when you take architecture and operating systems. But for this course, this gives a sufficient approximation for everything. Now the reason I'm pointing that out is sometimes we'll take these timings and it will look very weird, like we'll be bouncing up and down a lot. Just know that there's a lot of problems with this approach, but in general you're going to get a good approximation. All right. This can be a little confusing how to do it, so I just wrote a template code. It's here in the slides. By the way, if you jump over to your class code directory, I may or may not have committed this yet, you have something called timingtemplate.c, which has the code right there. So you should have access to this C file whenever you wish to take timings. All right, let's just look through this real quick. You have includes at the top IOStream for printing, and then time.h for taking your timings. Start off with main. The first thing you have to do is create two variables, the start and the difference. Notice they're of type clock. And then double is going to be our amount of time we wish to take. All right. Any questions yet? Straightforward? Good. The for loop is the first time you will probably have to manually edit the file to make sure its range is correct. And it'll make a little more sense when we start coding. But the for loop is how you want to, what sizes you want to run your algorithm for, and what jumps between each run. And so inside the for loop, the idea is each iteration of the for loop is a single test running your code once with a certain size. So you want to start the clock, that's start, and then function call to your algorithm. Ooh, your algorithm. It's right there. Pass in I or whatever else you need to show the size. And then diff to give clock minus the start. And then this next is the basic calculation in order to go from those two clock times into an actual time amount, and then we print it out. Oh yes. And don't forget to flush. The reason for that is if your program's taking a long time and you Control-C it, you will probably get no time outputs even if you have some of them. But flush, just make sure it's dumped to the file. So never forget to flush. Everyone got that?
Yeah.
Okay, good.
Smart.
Yeah. All right. Go back into timing. We're going to go and copy the timing template, and we'll just go timing-first.c. All right. Function to call your algorithm, I'll just make it simple and passing an I. And then I'll go up here and make a, I don't know, void simple int I. And this will just be int sum equals 0 for int. I don't know why I called this I up here. We're going to call it n. Int, wow, I equals 0. I is less than n, I plus plus. Sum plus equals I, and we're done. So that's going to be the whole function. Okay. Simple summation. G++ timing first. If we run it, hey, look, it's spitting out a bunch of data. Go ahead and dump that to a data file. All right, good. Data.out, and it has a whole bunch of information. All right. I think I went over this really fast, so let me make sure it's clear how it's printing it. Notice it first prints out the size, and then it prints out a space followed by the time amount in seconds. All right? Okay. So in this example, I did the first is the size in 1,000, and the second number is the seconds. Okay, it's pretty small right now. This probably looks close to the output I just got earlier, so that's great. How do we plot this in Gnuplot? Well, we saved it to some file. This one was called simple timings in these slides. I think I called it out. Is that right? Data.out. So if you're inside Gnuplot, you can do graph the timings with here. Well, you know what? Let's not reinvent the wheel. Let's just copy over our simple over here. I'm going to go and open up simple.plot. But this time, instead of plotting sine of x with line, I'm going to do colon, colon, single timings. All right. So colon, colon, and I called it data.out with line. So now if I type in make, boom, there it is.
And what is this actually plotting?
So what this is plotting, on the bottom is the size. Remember in the output, it would print out first the size that it ran the algorithm. So this is at 100,000 passed to that function, 200,000 passed to that function, 300,000 passed to the function, 400, 500, 600, 700, etc. is the bottom. That's the value passed to that function. And then on the left is the amount of time that function took to complete.
It automatically knows what scale to use.
Yes, Gnuplot actually will do that for you. And you can specify it explicitly if you want to. I'll show you that in a moment, because sometimes that is very useful. Now, keep that graph in your mind. And the reason I tell you that is I'm going to rerun this. Whoops. And I'm going to show you, make the plot again. Is that the exact same graph? No. Is it very close? Do you see how the pattern is still basically a straight line, but it's going up and down a bit? That's what I'm talking about. There's problems with this approach. It's going to cause some, what I call jitter, is the official term here. And it's, because normally you would think theoretically it'd be a straight line, but there's some jitter, some artifacts inside of it. That's okay. Don't worry about that. It's still pretty close to what we want it to be. Okay. Now, let's say we had, what was it? We had a dot out. I'm going to move a dot out and call it single sum. And I'm going to open up our test again. Let's see. Timing first. And this time I'm going to for int j equals 0, j is less than n, j plus plus. So is that going to be slower?
Yes.
By how much?
0.001.
All right. We're going to go ahead and I just wanted to see what you said. That's all. Timing first, a dot out, and this time we'll call it to data2 dot out.
I'm pretty good with this.
You're pretty good with the numbers? Oh, okay.
Yeah, I was pretty close with the hot dogs.
Okay, you were pretty close with hot dogs. And you see it's already taking a while?
Yeah.
Like I
Yeah.
said, so it's gonna probably take 2 seconds. 5 seconds.
1,
7 seconds.
2, 3,
12.3.
4,
complete our lifetime.
5, 6. So okay, this is taking a while. I'm going to stop this. Let's see, did it actually give me data? Oh, it gave me data.
2.6 seconds.
Oh, wow, look at that. All right, let's go and edit the simple.plot real fast. And instead of taking data, just regular data, we'll do data 2. Type and make.
Exponential.
No, it's not exponential.
Exponential.
No, this one's not. Can anyone see what that is? This is actually a really clear, pretty clear graph.
No, it just kind of goes up.
The thing you want us to avoid.
No. This is not exponential. This is not intractable.
It looks like
No, no. If it was exponential, the graph would look something like this. It would go, I'm good, I'm gonna go, is what it would be. It would just go skyrocket straight up, almost vertical if it was exponential. But this one's not going vertical. It hasn't gone vertical. It's actually not going to go vertical. It's not going to go vertical. Can anyone guess what this one is? Actually, look at the code, look at this graph.
Is it quadratic?
Yeah, quadratic. This one's quadratic. Okay. All right, well, that was interesting. Let's see if I go into simple.plot. I think I can do 2 of them, is that right? Yeah, good. So we just do it with a comma. So we're going to go data 1 with line, comma, and do I need to do the quote thing again? No, good. Data 2 dot out with line. Save that, make. Wow, what, oh, that was good. All right, can anyone see the lines?
the one line.
I can
One.
see one.
You know where the purple one is?
Behind the
It's down here. Yeah. Wow. So, which is better, quadratic or linear? Linear. By, now I'll ask the question again. By how much? A lot. Yes. The answer is a lot. Okay.
Can we see exponential?
The problem is I can only do like up to around, I don't know, 20, and then it's game over. It's just game, like, if I showed you exponential on this one, on this graph, this quadratic would be down here as well, and these numbers would be insane. You know what? Let me see if I can. I think Google.
Yeah.
Let's go with Google here because it's really something that would just take me forever to show you. Let's see. Big O exponential. Oh, I totally spelled that wrong. Versus quadratic.
Yeah, Google knows.
Google can figure this out.
See, look at that.
Polynomial time. Ooh, Stack Overflow. Man, how could this possibly? Good. It sends me to Wikipedia. Stack Overflow to Wikipedia. Oh, this is great. Huh?
Do you not like Stack
Oh, I love Stack Overflow. Oh, and they don't give me a graph? Oh, Wikipedia, you're failing me. There we go. Boom! Oh, this is a beautiful graph.
Wow.
And in log n, which is actually not bad. It looks kind of bad here, but it's really not. There's n squared, and there's 2 to the n. It looks like there's not much difference here, but it's a pretty insane difference. This one's just showing you all of them. If we were to blow this up and just compare 2 to the n to n squared, this line would be down here, and n squared would, 2 to the n would look basically the same, and these numbers would have, well, it'd be, 2 to the whatever. It'd be giant exponential numbers. Also, hopefully this shows you that 2 factorial is actually worse than exponential. That's right. You can get worse than exponential.
Go backwards.
All right. And now hopefully you can see log base 2 of n is pretty good. And actually square root of n is not bad either. All right. So hopefully you can see today analyzing algorithms analytically to predict performance. We did that last class, remember, with Big O. Everyone good? Remember Big O? All right. Profile code to find the piece of code that's a bottleneck. We did not do that today. Hopefully we'll get to that. And get and plot timings to see actual performance. We did do that, so you can actually see the performance of different algorithms. We're going to stick to the basics in this class. I could teach a whole class on trying to do real-time analysis or analysis of algorithms. Either of those subjects could be a whole class, but that's not the point of this one, for this class. All right. I just wanted to alert you to a couple things that help, but specifically a couple of tips I want to give you. For example, we just saw this. You know, you have two algorithms, but you can't see it. But if you notice, your data, your x-axis is usually because it's too small to see. There are different ways to do this. You can try and set the x-axis. So that would be with the :2. So if you notice, simple.plot. I just did : : That means it's going to automatically, on the x-axis, figure out what it wants to be. You can set these manually. So if on the y-axis you want to go from 0 to 0.5, and then type in make. Now it goes from 0 to 0.5, and you can kind of see that green line now, right? You can go ahead and make that even smaller. All right, looks like I'm going to make it really small for this to come out, but that'll help you zoom in and out to try and figure out what's going on. And obviously you can do the same thing with the x-axis. We did not do profiling, so forget that for now. All right. I will have to admit, Big O is actually a really big subject. It can take a while to understand what's going on. I did give you an assignment. I did give an assignment on Big O, right? Great. So get started on that. If you have questions, please email me. You probably will. This assignment is actually exceptionally hard. Some of them they may look easy, but quickly you'll figure out, wait, what does multiplying by 2 on I actually do? If you have problems, please ask me. I'll try and help you out. We haven't done profiling, so we can do that later. It is important, at least in this class, to do empirical runs to evaluate performance. This is to really hit home the performance differences of code. Hopefully you can see that a linear algorithm is far superior to an n-squared today. And do understand that there's always anomalies that will not be addressed in this class, but there are little anomalies, jitter, that's going to occur. If they're minor, just ignore them for now. It'll make sense when you check your OS. But if they're giant anomalies, like sometimes back in this graph, let's close this and let me open up simple again. Oops, was it? Nope, I don't remember what the commenting out was. If we just did data, sometimes it's pound. I don't know which one it is in this one, but that's okay. Type in make. You know, this is normal jitter, but if you were going along and all of a sudden it went all the way up and then all the way back down and then came back up, yeah, that would not be expected. Notice how with this one, you could kind of make a nice linear curve underneath it. And you could kind of make a nice linear curve above it, or maybe a little goes above. Going a little up is expected. That's just added time. But jumping down is not expected. So if there's any big changes, that is probably some problem in your code or something going on with your algorithm. All right. Any questions on this? Good. All right. We're going to finally get to coding.